Great, we can see your slides once you make it full screen, and we already know we can hear you. Let Graham introduce you, and then we can get started.
No,
Sorry, slideshow, yeah.
I see.
Yep, we can see them just fine.
Great. Hi, everyone. Welcome back. We have our next speaker this morning, Xialong Li from the University of Delaware. Over to you, Xialong.
Hello, yeah. Hello, everyone. I'm very glad to see everyone. And I'm a graduate student at University of Delaware. Today, I'm gonna talk about the work we just submitted about searching for light echoes, considering the application of deep neural networks. And the current LSST pipelines is mainly focused on point sources. One of the very important phenomenon it's missing is the light echoes. So what is the light echo? So light echo of transient is the reflections of the transient event on the interstellar dust. Like imagine that there's a transient event and the Earth are two foci of this 3D ellipsoid, and the light from the intersections of this dust streak and the 3D ellipsoid arrive the Earth at the same time. And if the dust is uniform distributed everywhere around the circle, we can observe a circle around the source event, like the on the right image. This is the light echo from supernova 1987, and but in most cases we can only observe part of the light echoes. This is because only a portion of the dust distributed around this 3D ellipsoid. So why light echo is significant for astronomy? Because the light echo give us second opportunities to study historical transient, like the transient we discovered several hundred years ago. And by study the spectra of light echoes, we can classify historical transient even we did not have the spectrum directly observed. For example, the supernova Tycho was classified as supernova type 1a after studying the spectrum of its light echoes. And by studying the light echoes at different directions, it enables a 3D view of astrophysical phenomenon that is otherwise impossible for us at our point on the Earth. In this image, this is the three light echoes at three different directions for class A. And the study of those light echoes confirm its asymmetry. And the light echo is a time evolving event. The evolution of this series of images from May to December 2002 reveals the dust structure around these variable stars. So, but how do we search for light echoes? The current way to search for light echo is relies on human visual inspection thousands of images. There are currently two surveys, that Atlas and DECAM, that discover some light echoes from more than 200,000 images. So the challenge is light echoes are diverse and the time evolving. It's very faint and diffusive, and there are lots of artifacts and false positives in the images from the telescope. And at the scale of LSST, the data volume will be 10 times larger. So this because the human visual inspection becomes unfeasible. And we need automatic data mining techniques. And in this work, we explore the application of object detection model, the YOLO, which is a famous model developed by the computer vision community that can detect the object within an image. For example, the YOLO take the input image and pass it through a neural network, convolutional neural network, and make predictions for the object bounding box. This include the class of this bounding box, this object, and also the coordinates of 4 coordinates of the locations. The dataset we prepared is the light echoes we discovered from the Atlas telescope. We searched more than 200,000 images and find light echoes at about 17 fields. And the images is split to about 20 arc minutes each image that contains light echoes. And we label 3 classes for each image, that the light echo, stars, and some other artifacts. We use the flip and rotation at 3 angles to extend our dataset, and we end up about totally 240 images. Because unlike the object we see in the image in daily images, the light echo is an extended feature. It has no clear boundaries, and the labels is kind of arbitrary. For example, for this light echo, we can label the whole continuous pieces as an object, or if we can label multiple small bounding boxes. And this makes the evaluation complicated. To solve this problem, we define IOP. This is by the overlap between the predicted bounding boxes and the labeled bounding boxes, and divided by intersection is the overlap, and divided by the area of the predicted bounding boxes. Like if the red is the prediction, and we labeled all continuous features as light echo, and when the red one is inside this white bounding box, the IOP is 1, and we consider this as a true positive detection. So the true positive detection is defined as the score threshold. It has the classification score that is larger than the threshold, and also the overlap, the IOP is larger than a threshold. And from the true positives, we calculate the precision and the recall. The precision, which means how many predicted objects are correct, and the recall means how many labeled objects in the test set are being detected. So as an example, in this image, there are those 3 red boxes are true positives, and while the other one outside the labeled bounding box is false positive. So for our model, this plot shows the results. The first panel is the overlap and the classification score. the bounding boxes pass the classical classification score marked as the orange region but have the IOP below the threshold is the false positive, while the above the threshold is true positives. The middle panel shows the true positive versus the F positive or the rock curve, and the right panel shows the precision and the recall curve. From the precision and the recall curve, we can see that if we choose an overlap threshold larger than 0.1 and at the score 0.4, we can detect 70% of light echoes at a precision of 95%. So there are some challenges for this model. The first is the overfitting, because our data set is really small at this moment, and AI models are likely to overfitting to current training set. And other limitations include that the labels is made by visual inspection, and the bounding boxes are not accurate. And in the future, we are considering to create light echoes from the simulations, and this might improve the performance, and also considering the time evolution, extend our model to a series of images, and this can also offer the opportunity for improvement. And this brings to the end of my presentation. Thank you very much for listening.
Thank you, Xiaolong, for a really interesting talk. We have time for questions. Who would like to start? Yeah. Question here from Armin.
Hello, thanks a lot
Hello.
for this excellent talk. I have a question. You said the bounding boxes are done visually. How don't you have to do this automatically for all of these images?
Those bounding boxes are need to use the label tools to draw the bounding boxes, and draw the coordinate for each object.
Oh, you're doing this only for the training set, and then later on for all of the images you do it automatically. Is this correct?
No, because each light echo is a different creation, different shapes, so we need to label each one separately.
Okay, thank you.
Yeah.
Hey, Xiaolong, great talk. Melissa Graham showed us yesterday that there were interesting artifacts in Rubin, things like wisps and claws that were extended structures. How well will your algorithms deal with these kinds of image artifacts in Rubin?
For the Atlas, our data set is from the Atlas telescope. The artifacts include star streaks like this. We currently made labels for anything that is not a star, not light echoes, and in our paper we showed that after extend this to a larger data set, this could reduce. There are still some artifacts, but after making labels for some of them, this can reduce by about 70% when we set the class score to 0.2. So yeah. For the Rubin, yeah, we expect that the image quality will be much better. So
Great, thank you. Would anyone else like to ask a question? No, looks like we're done here. So let's thank Xiaolong again for a great talk.
thank you, everyone.